Alright, good morning everyone. Welcome to the new chapter 11, known as the DC circuits. So what does DC circuits mean? First of all, DC represents direct current, which means that for this kind of circuit, current only flows in one direction. Now this also means that there are also certain kind of circuits that whereby the current flows in multiple directions. Those kind of circuits we call them an AC circuit, or we also call it alternating current circuit. So a DC circuit, a direct current circuit, is very simple. Basically, is what we have seen before, all the way from your lower sec science. So let us just recap. When we deal with a circuit, we will always draw or use a circuit diagram, which is a simplified diagrammatic representation of an electric circuit to show the connection, between electrical components. So for example, this is how it looks like in real life, an example of an electric circuit, and how we will represent that on a diagram will be as such. For example, this will represent a bulb, this will represent an ammeter, right? And then of course our battery with the longer vertical line representing the positive terminal. So for the first part, right, where we are trying to learn about current, potential difference, and resistance, how are they related in a series circuit? These are the following learning outcomes. So knowing how to draw a circuit diagram, and knowing how the current changes in a series circuit, how the potential differences behave in a series circuit, and how the resistance as well changes. So this is how electric circuit in our home, right? It can function either as a series circuit or a parallel circuit, which we have already learned in lower sec science. So if you take a look closely at how the currents are flowing, right? So let's say for the series circuit, now when the switch is open, take note that the electrons within the circuits are already present, right? Just that when there's no when the switch is open, the electrons are stationary. So if they are stationary, no one is doing work in the circuit, so the light bulb will not be able to light up in this case. But when the switch is closed, right, the battery gives the electrons energy to move through the circuit. That's what is shown in this diagram. And you can see that the currents are all moving in one single direction. Now on the other hand, if you look at the parallel circuit, right, the battery again is providing energy for the electrons to move within the circuit. And take note, right, let's say for example the red lines, the blue lines, and the green line, it represents the total amount of current that are moving through this part of the circuit, right? And what happens when it passes through one of the junction, right? You will notice that the green one will only be the electrons entering this junction, and the rest of them will continue to pass through, right, until they go to another junction, and then the current splits again, right? This is what happens in a parallel circuit, whereby the total current coming out, or rather the total current that are present in the main branch, right, when it goes to a junction, it will just split themselves. And how will they split? They will split based on the resistance that are present in each of the bulb, right? Sometimes if let's say the bulbs are they have the same resistance, if the bulbs all have the same resistance, let's say for example 2 ohms, right, then they will split, the current will split themselves equally in each of the branch. And of course, if I have more resistance in one of the branch, if the resistance, let's say for the first one is 5 ohm, right? If now it's increased 5 ohm compared to the rest 2 ohms, then the current that it receives in this particular branch will be less, right? Because more resistance, less current. There are more obstacles for the current to move, so obviously there will be less current moving through this particular branch. So are you able to give an example, right? Since we use both series and parallel, where can they be found in our uh, houses, right? Which part of the circuitry in our house uses series, which part of it uses parallel? Okay, now just to recap, right? These are some common symbols that we use to represent electric circuit. So the common ones are your light bulb, a cell, right? And where multiple cells becomes a battery, and a fixed resistor, which means the resistance that cannot change its resistance, right? The resistance is fixed. On the other hand, you also have a variable resistor, right? That you can change the resistance readily. And another one that perhaps will be more important now will be the ammeter and voltmeter. If you look at the next part, there are in general 3 different kinds of circuits. Okay, one is a closed circuit whereby there is the wire is connected at every point, and you can see that this allows the current to move through. This allows the electrons to move a complete round. Right. On the other hand, you will have a circuit that is open. Right. Because of this, electrons are unable to move through the wires. So then there will not be any current running through the circuit. Right. But that being said, there is still EMF, right? Because of the presence of the battery, there will still be EMF, right? If let's say I decide to put a voltmeter across the battery, I will still get some reading out of it. Just that if I put a ammeter, let's say over here, I will get 0 ampere. Now, what happens, right? If let's say I have a normal closed circuit and I decide to be very mischievous, right? I put a wire across. Okay, now you think about it, if you were the electrons, right? If you were the electrons moving through the circuit, would you take a shortcut to get back to where you came from, or would you take a longer path if given a choice? Right? And you think about just now the example that we had, usually the larger the resistance, right, in one of the branch compared to the other, if there's a larger resistance, there will be less current moving through. So in this case, if I put a wire across, and we're gonna assume that this piece of wire, right, is an ideal wire, right, with 0 resistance. So in that case, if I'm the electrons, right, I would choose to all move through this path, right? I will bypass the bulb altogether, right? I will instead all just move through this part of the circuit, especially because over here the wire has 0 resistance compared to maybe a bulb that is non-zero, maybe let's say 2 ohms again. Okay, so in this case, this phenomenon is what we call a short circuit, right? Whereby uh, there's a presence of a short circuit path with a very low resistance or least resistance. So this happens in real life. If let's say the wire in a appliance, right, breaks and it connects to a path with lower resistance, then the current will travel through that path. Okay, so this is another example of short circuit. Right, now I want you to observe, right, how does the current and voltage behave at different parts of the circuit. So this is a video, we're gonna take a look now. So now I'm gonna connect the circuit, and if you look at this represents the electron flow, right? So this red one represents the conventional current. The blue one represents the electron flow. And let's say now I'm trying to test for the potential difference at two different points, right? You see that when I put across 2 points, right, where the bulb is located in between, I will get a non-zero voltage reading. That means over here I'll get 4.5, for example. Right? If let's say now I put between this point and this point, I will get a voltage of 4.5 as well. And what do you notice when I have the 2 points that are 4.5 volt? That's equivalent to the 9 volt of EMF, right? Okay, which means that the voltage, right, or the potential difference, or the energy that's given by the battery is now shared very equally by these two bulbs with the same resistance. Right, and on the other hand, if I measure the current at different juncture, you will see that it remains the same amount of current. Why? Mainly because there's only one path for it to move through, right? So obviously the current has to be the same throughout the circuit. Okay, so feel free to rewatch the video, right? You can scroll back. I'm gonna play the video all at once for you to take a look. You can enter, you can scan the QR code in your notes, um, to access this simulation as well. Okay, so this one is to measure the current. Take a look again. See how the current changes at different point of the circuit. Right. So based on this video, the conclusion that we get is that the current at every point for a series circuit is the same. Okay, because there's only one path for it to move through anyway. So the current has to be the same. And what happens for the potential difference, right, for each of the resistor? So just now the example you saw is when the potential difference are the same, mainly because the resistance are the same. But what if, right, R1 and R2 are different values? Okay, so in general, the higher the resistance for a series circuit, the higher the resistance, okay, the higher the potential difference will be. Right, that's the general rule. Because higher resistance, you will have to use more energy from the battery. Okay, but the key conclusion is that the total EMF, the total energy, right, per charge from the circuit will be the sum of the potential difference across all the components. Okay, so if let's say if I look at this series circuit, using all the information that I know, right, where the V E, which represents the voltage on the EMF, right, is equals to the sum of the individual potential difference, and I know that V has the relationship with I and R in this format, V equals to IR. So if I were to translate this, right, if I were to do this in terms of this kind of form, and I know that I1 and I2, right, the current that passes through this resistor and the current that passes through this resistor, they are the same, right, they are the same value, so I can just use the same letters. Let's say I. Now if I factorize out the common factors out of this expression, right, I will get I equals to R1 plus R2. Now what's the concept behind this, where VE, the sum of my, or rather the EMF, is equals to I times the sum of these two resistors together, right? This is equivalent to me having a circuit where, right, I have the same EMF and I have one big resistor whereby it's made of R1 and R2 together, right? So this is what you get when you put two resistors in a series circuit. You will just get their effective resistance, right, the sum of the resistance together. So RE equals to R1 plus R2. Okay, this is what we call the effective resistance as well. That is why you see it as RE. Okay, so take note, in physics we usually use this subscript, right, in a way to name our variables, because all of them are R, right, but they are not the same value. So how can we differentiate them? We will use these subscripts. So RE equals to R1 plus R2. Okay, so this is the key summary for a series circuit. Pretty consistent with what you have already learned in lower sec science. Okay, so let's use a work example to illustrate this concept. Now I'm given two resistors with the value 1 ohm and 2 ohms connected to 1.5 volt battery. Calculate the effective resistance. So effective resistance in this case for series circuit, this will just be the sum, right? The sum of individual resistors. So effective resistance will just be, for series, 1 plus 2, 3 ohms. Now 1b, the potential difference across each resistor. So let's say what is the potential difference between across the first resistor with 1 ohm, right? I use a subscript to denote the voltage or the potential difference for the first 1 ohm. So I know that is equivalent to the current times the effective resistance. The resistance of the 1 ohm. So what will be my I value? Will I be able to find it? How can I find my I? Okay, so I know that the current for every point of the circuit for a series circuit is the same. So I can also find that by taking the total EMF first divided by the effective resistance. So this will give me 1.5 divided by 3. Okay, so I will get 0.5 ampere. So in that case, I know what's my I, which is 0.5 times the first resistance, which is 1 ohm. So I'll get 0.5 volt for the potential difference across the voltage of the 1 ohm resistor. Now, next one, I want to find the 2 ohms one. Right, so same thing, I times R of the 2 ohms. In this case, 0.5 times 2, right, I will get 1.0 volt. Okay, alternatively, right, again, I know that the sum of my each of this voltage, right, the sum of which must give me 1.5 volt. So I could just also alternatively voltage of the 2 ohms will just be 1.5 minus 0.5, the voltage that I found in part A. So this will also give me 1.0 volt. Okay, question 2. The 2 ohm resistor is replaced by an unknown one with R resistance, R ohms, and the current flowing is found to be 0.1. So this has been replaced with R ohms. What is the value of R? Okay, so again, we go back to the basics. What values do we have? We have the EMF, and we have this 1 ohm, we have this R ohms. Okay, and what are we trying to find? We want to find what is the value of this R, and we have the value of the effective resistance, effective current, or the total current from the circuit. Okay, let me name it as IT. So in that case, I will use VE equals to I times R, right? The total current times the effective resistance. And I know 1.5 has to be equals to 0.1 times 1 plus R, since my effective resistance has now changed to 1 ohms and R ohms. So can I solve this equation? Right, I can. 1.1 plus R will be equals to 1.5 divided by 0.1. So 1 plus R equals to 15. R equals to 16. Sorry, 14. Alright. Okay, take a look at the answers. Feel free to go back to the video if let's say you are unsure how to get all these values. Okay, so can you attempt this homework question as well for your HBR? Thank you. Alright, now going to another part, right? If you think about your real life, you always see your batteries arranged in such a manner whereby the positive and the negative terminal, they are arranged side by side, right? Positive to the negative of the other battery, right? And why do you think they are arranged in this way? Is this a series or parallel? You can make a guess. Okay, actually this is an example of a series arrangement within remote control. So what's the point of this? So that my EMF, right, will be the sum of the EMF from each of the battery, right? So for example, the VE here will be equals to the voltage of, the EMF of the first battery plus the second battery. So if they are the same, let's say, did they say what is the voltage of the battery here? So typically, uh, let me see, voltage of AA battery. So it's usually between 1.2 to 1.5 volt, right? So in this case, this will give me a total of 3 volts of energy within this remote control. So typical voltage of a AA battery. The next part of the video, okay, we'll be looking at a parallel circuit. Right, these are the learning outcomes for a parallel circuit. Again, we are just seeing how the current, how potential difference, and how effective resistance will change in a parallel circuit. Right, now look at this slide about the fairy lights. Okay, I'm not sure if you use fairy lights at your house, right? Typically it's used as a decoration. And here are comments by 3 separate students. So A says that if a bulb blows, the rest of them will not light up. Okay, B disagree because if one bulb blows, the others will still light up. C says it depends on how the bulbs are connected. So if you have used fairy lights before, you should notice that sometimes when 1 or 2 bulbs blown, right, not all the bulbs will blow or will not light up also. Maybe let's say these fairy lights, right, they are connected. Sometimes you will see one of them blow, but the others will still light up. So what does that tell us about the arrangement of the circuitry in the fairy lights? Is it series or parallel? Okay, so you should notice that it's mainly parallel, because if it's series, then there's only one path for it to flow, for the electrons to flow. So if there's only one path, then it will cause a lot of trouble, right? Because the other subsequent bulbs will not be able to have any energy for the electrons to move. So here is for you to watch a video on how parallel circuit works. Okay, I'll attach this in our Google Classroom. Okay, so pause the video, go and watch it first. Now, so for a parallel circuit, right, the components are placed next to each other in parallel, and the ends are connected like the rungs of a ladder. So, right, you will see how the currents on the charges, the electrons, right, when they come to a junction, they will split themselves, right, depending on the resistance of the bulb. So the main idea is that if this are some amount of currents, so let's say this is I1, right? Let's say this is I1, and the other side of it, right, is I2. When they speed up, right, and then when they meet back together, and as it travels back into the battery or the cell, sorry, let's say this is IT, total. IT stands for total. Right, then the total current that I should be getting back is the sum of the current in each of the individual branch. Okay, right, the sum of the individual current each parallel branch, right, the total current should be equals to that. And if you think about how does the potential difference behave? Okay, just now if you think about your series circuit, the video that was shown, right? When the uh, if I take the potential difference across the same part of the wire, right, whereby there's nothing in between, no resistance, right, I should be getting a 0 volt if I put a voltmeter across it, same part of the wire. So same thing for the parallel circuit, right, to the electrons or to the circuit. All this part with no components in between, there's no resistance in between, the potential difference, right, will be 0 volt. Let's say if I take this part and this part, right, I measure what will be the potential difference. This will give me 0 volt because there's no components in between. Okay, but if I were to take this and this between the bulb, or rather sorry, the bulb is in between, then I will get a non-zero reading, and you will notice that this reading will be the same as it comes out from the EMF. Same, right? And likewise for the other bulb, because to the circuit, right, this part to them has no potential difference, so it only matters when it goes to the other side of the battery. Now what this means is also saying that the potential difference, right, across parallel branch, right, these are parallel branches, they will share the same EMF, or they will share the same potential difference. They will give you the same potential difference reading. They take in the same amount of energy from the battery. Okay, so this is what's happening. Okay, this is I1, this is I2. So the sum of the individual current will give me the total current. Okay, then same thing for a parallel branch, right? So for a parallel branch, right, this is how the current travels. Right, this is the path that it travels. So to them, uh, the potential difference across each of the resistors, they are the same. So VE equals to V1 equals to V2. And we're gonna use this relationship, right, to derive how the effective current will be. Or simply put, if I want to combine these two resistors together, right, if I want to combine these two resistors together, what would I get in terms of just one? If I were to draw, right, if I were to combine the two resistors together, what do I get as just one resistor? So we're gonna use what we have learned to derive how the effective resistance behave for a parallel circuit. Now, so we're gonna use what we have already known, which is the total current is the sum of the individual current in each of the branch, and we're gonna make use again this V equals to IR relationship, because this is always true no matter what arrangement you are. So since I is equals to I1 plus I2, right, I is equals to V over R, so I'm going to apply this to the relationship that I know for certain for parallel circuit. So this will be equal to V1 over R1 plus V2 over R2. Now, V1 and V2, if you recall for parallel circuit, V1 and V2 are the same, as they draw the same amount of energy from the battery. Okay, so this means that I can substitute that as VE, since they are the same value. So I is equals to IT, right? The total current is equals to VE over R1 plus V over R2, and I can combine them, right? So this becomes R1 plus 1 over R2. Now, if you look at effective resistance based on this formula, right? R is equals to V over I. So for me to find effective resistance, what I need to do is to find the total voltage divided by the total current. So let's see what happens when I take VE over IT. Right, this one I move it to the denominator. This one I have to move it to the opposite side. And how can I do that? Right, is equals to 1 over the entire 1 over R1 plus 1 over R2. Right, this itself is the effective resistance of a parallel circuit. Right, if I were to put it simply, if effective resistance, or aka RE, right, this will just be 1 over the reciprocal of each of the resistance. And if I would want to present it more elegantly, right, 1 over RE is equals to 1 over R1 plus 1 over R2, right? Depending on how many resistors you have in each of the individual branch, you can continue. So if this is only 2, then it will stop at 2. So this is how the formula is like for parallel circuit. Okay, so in general, these are the relationships that you need to remember. For the parallel circuit. Right, so this is a comparison. If you look at how different series is, if the resistors are in series, you just sum them up very simply. If it's parallel, you just need to do some magic, right? The reciprocal. So reciprocal just means 1 over something. So 1 over R just means reciprocal of R. Okay, current, because the current will be the same, I1 equals to I2 equals to I3. Any point of the current for series is the same, but for parallel, the sum of the current in each of the branch is equals to the total current. And lastly, PD, PD will be V E equals to V1 plus V2 plus V3 if they were in the same series circuit, right? As compared to VE equals to V1 equals to V2 equals to V3, right? For parallel. So you can see actually they are pretty similar, just that their current remains the same for series. Current is just a sum of everything for parallel. Then they switch over for the relationship for V. I1 plus I2 plus I3. Okay, you can watch this video yourself. So observe how the brightness is affected in a series versus a parallel circuit. Right, you will notice that for parallel is brighter because the EMF measured is greater. Right, brighter than if it was placed in series. So what are the, after watching the video of the two bulbs in a series and a parallel circuit, okay, for in terms of brightness of the bulb, you can see that clearly the one in the parallel circuits will be brighter. Right, this set of slides will show the summary between a parallel to the series circuits. Now, in terms of what you need to copy down, okay, these are the things that you need to write in the table. So for the first one, in terms of brightness of the bulb, so parallel will be brighter than the ones in series, okay, because the voltage is identical to one another in the parallel branches. So if you are unable to visualize here, go and draw a diagram maybe at the side to compare, let's say the one in parallel versus the one in series. Okay, so this is parallel, and then you draw maybe another one at the side that shows a series circuit. So these bulbs will be brighter because the voltage across each of the bulb will be the EMF of the cell. As opposed to the series, it will be half of it only. Okay, second one, in terms of how the currents will behave. So for series circuit, the current will be V divided by 2R, because 2R is the effective resistance. Right, for the series circuit. Okay, so imagine this one bulb has a resistance of R. Okay, on the other hand, the current will split for the parallel branch. So in that case, the current through each of the bulb will be V times R only. So which one is bigger between these two? If my denominator is a smaller number, 2R versus R, right? R is smaller, so then this gives me the current to be greater for the one in parallel. So this also tells us that, okay, the current drawn from a parallel circuit will be greater, right? And this is why we don't put in too many plugs in the adapter. So if you've seen your house, right, those kind of 3-pin plug adapter with plugs at different sides. So maybe one on the left, one on the right, and one in front, right? Why is it recommended that we don't connect another adapter to it? Right? Maybe some of you like to connect a lot of different some of these plugs to extend the number of power sockets, right? But we don't do that because it's equivalent to adding more components in the parallel circuit, and this will cause more currents to be drawn from the power source. And then the power source will first of all deplete quickly. So let's say if I'm connected to a cell, it will the energy will run out faster, right? And then on the other hand, if there's more current drawing out from the circuit, it will cause a lot of heat in the circuit. That might even cause a fire in that case. Okay, for the last one, right? If I have bulbs placed in a series, if one of them blows, right, you can be rest assured that the other one will not work as well, because if it blows, it's basically become an open circuit. So there's no other path for the charges to move or the electrons to move. But parallel, because if one blows, right, the electrons can still take another path for it to move. Okay, so these are the summary of series versus parallel, the advantages and the disadvantages. Go and try the work examples yourself first. Okay, we'll go through them in class. Okay, some clues on how to solve this kind of question, right? Finding the effective resistance of all the resistors here. So one key item, right, or rather one skill that you could use is looking at this in terms of one resistor, looking at this in terms of another resistor. So from what I see, I can package this as one resistor, which I will use the 1 over RE, right, to find the effective resistance for these two first, this 3 ohm and 6 ohm. Then after that, I look at them in terms of two resistors connected in series. So this is one package, this is another, right? That way you can find the effective resistance. Okay, same for this. You can think of this in terms of one package and the other package like this. So maybe you can calculate the total resistance for these 3 ohm and 4 ohm, right, as if they were connected in series. I mean, they are connected in series, right, for these two, and then after that parallel to this 6 ohm. So try it on your own first. Right, with that, you can now try and attempt a full question. Okay, after you know how to calculate the effective resistance of this kind of combined circuit, where it involves a parallel plus a series. Okay, we will go through that in class. Please attend this as part of the homework as well. Okay, we are done with the DC circuits. This is the overview, right? Learning about series, which we are probably quite familiar with, then a parallel circuit. Right, now think about some of the wearable electronics that you have seen or worn, and how do you think these wearable electronics have impacted our daily lives? So, for example, an Apple smartwatch, right? Even for Mr. Wong myself, I wear one, and I use it extensively for fitness, for health, for many reasons, right? And the advent of all these electronics, right, really came from our understanding of how circuits work, right? Of many decades of like research in physics and electronics. So hopefully you can be the next um, engineer to produce the next generation of electronics.